Hello students, today we'll see Turing machine. How do we define a Turing machine? A Turing machine is one of the modified version of a PDA, and we can say it is much more powerful than our PDA. Why do we call it as much more powerful than the PDA? In a PDA, we use a stack, whereas when we come into the Turing machine, we have a tapes to store the symbols. That Turing machine is a generalized machine which can recognize all types of languages. We know which all types of languages we have: type 0 language, type 1 language, type 2 language, type 3 language. So type 3 language is our regular grammar. We have a context-free language. We have context-sensitive language. Apart from these languages, the Turing machine also accepts the language generated from type 0 grammar. That is also called as an unrestricted grammar. Coming to the definition of a Turing machine, first we'll see the generalized model of a Turing machine. See here, if we see here, the model of a Turing machine consists of three components. That is tape, read-write head, and a control unit. So what is the duty? What the Turing machine is going to have in a tape? If you see, the tape is further divided into cells. You can see here it has been divided into cells. Each cell will consist of one input symbol. If you see, only one input symbol is there on the each cell. The strings to be scanned will be from leftmost to the rightmost position. If you see on the left hand side, there are lots of blank space will be there. Even on the right hand side, it is going to have a blank space. Tape is of infinite length. So in a simple way, tape is, we have a tape. Tape is further divided into cells. Each cell will consist of one input symbol. Tape is of infinite length. Next, coming to the next component of a Turing machine, that is a read-write head. The read-write is going to read one input symbol where it is pointing to, and it can write to a tape to where it points. So what it is going to do, it is going to point to the symbol where it is going to read and where it is going to write. Next comes the next component is our control unit. The reading from the tape or writing into the tape is determined by the control unit. So what has to be read from the tape and what has to be written, it is the duty of our control unit to take care of these things. The different moves, whatever are the different moves that are performed by the machine, that is Turing machine, depends on the current scanned input symbol and the current state. As we know, which input symbol it is going to scan and which is the current state is there. The control unit always what it does, it consults the action table. We have an action table, that is a transition table, and based on that it is going to perform the task. The read-write head can move either to the left or to the right. As I have told you, it can move to the left side or it can move to the right. Movement can be on both the directions, left, right, left, right. It is going to move from left to right, right to left. What all are the various actions performed by the machine are: change from one state to the another state. The symbol pointing to the read-write head can be replaced by the another symbol. As we know, what we are going to do in a Turing machine is one input symbol will be scanned, and after scanning that input symbol, what it does, it is going to replace with the another symbol. We'll see further when we see the example. It is going to be more clear for you. The read-write head may move either to the left or towards the right, based on what transition we are going to define. As here, if you see, if we define how we are going to define the Turing machine, the Turing machine is formally defined into 7 tuples. The 7 tuples are m is equal to q, sigma, tau, delta, q naught, b, f. What does the q stands for? Q represents the finite set of states. Sigma is a set of input bits. Tau is a set of tape symbols. Delta is a transition function which is for the mapping q by tau to q by tau into, it is going to either, we have to tell the pointer where read-write head to move, whether it has to move to the left direction or right direction. So we are going to represent with L, comma R. L indicates left direction, R indicates the right direction. Q naught is the start state. B is a special symbol indicating the blank character. And F subset of Q is a set of final states. So we have seen that how to define a Turing machine. Then we have seen different components of a Turing machine or a model of a Turing machine. Next, coming to the representation of Turing machine. The Turing machine can be represented in 3 different ways. Which are those 3 different ways? One is by transition table, next by instantaneous description, next by the transition diagram. There are 3 different ways to represent the Turing machine. We'll see how do we represent in a transition table. The transitions of Turing machines, what all the transitions of the Turing machines are there that are represented by using the transition table. You can see, you can observe here, these represents the states, this represents the tape symbols. We have A, B, which are going to A will be replaced by X, and after reading that particular symbol A, it will be replaced by X. After reading the input symbol B, it will be replaced by Y. So if we observe from this table, we can observe that for each state Q, there is a corresponding entry from the table symbol from tau it is there. See, what does it indicate? If you check this transition table, you are in the state Q naught. When input is A, we are telling that change the state to Q1, replace A by X, and this shows which direction the cursor has to move. So it is telling that if you are in the state Q naught, input is A, we are telling that change the state to Q1, replace A by X, move the cursor to right direction. So here we are going to, if nothing is different, say for example, if you can see a dash is the which indicates that the transition for that particular state on that particular input is not defined. That is Q naught on B is not defined, Q naught on X is not defined. Coming to Q naught on Y, what we are telling, if you are in the particular state Q naught, and input is Y, we say that change the state to Q1, replace Y, and let Y be as it is, move the cursor to a right direction. This is how we are going to represent that in the transition table. State, input, what action has to be performed. This is a state. These are the inputs. These are the replaced variables, which variables you are going to replace, and what action has to be performed is represented in our transition table. This is how we are going to represent the Turing machine using the transition table. Next, coming to the instantaneous description. Instantaneous description is nothing but the moves made by the machine. So here, we are going to define ID in our PDA also. In the Turing machine, the ID defined depends on the 2 things, that is a whole string, not on the string to be scanned, current state of the machine it is going to define. A Turing machine, an ID of a Turing machine is defined as alpha q beta, where Q is the current state of the Turing machine. Given string is divided into substrings alpha and beta such that given string is obtained by concatenating alpha and beta. The read-write head points to the first character of the beta. Now, the initial ID is denoted by Q alpha beta, where Q is the start state, and the read-write head points to the first symbol of the alpha from the left. The final ID is denoted by the string alpha beta QB, where Q belongs to F is a final state, and read-write head points to the blank character denoted by B. See, what happens here is, if you see this example, what does he say is, how do we define an instantaneous description of Turing machine? Is, say for example, if you are in the state Q naught, assume that you are in the state Q naught, and the input symbol to be scanned is, and the input symbol to be scanned is, assume that 0, 0, 1. I'm showing with an example how we are going to tell alpha, beta, Q naught, 0, 0, 1. What does this indicate? You are in the state Q naught, input is 0. So we are going to tell what it has to do. For example, I'll tell it as the instantaneous description symbol is like this, as you are already you know. So Q naught on 0, what we are telling, replace 0 by X, move the cursor to the right direction, means it should be the right of the symbol where we are going to move. And then this will be remaining part will as it is 0, 1, 1. That is, if you see this one, alpha Q beta, left side of the state, whatever we have, we call it as an alpha, this as a beta. Right of that. That's why we say that alpha q beta. Initially, what will be there? Q alpha beta. That is, if you check here, Q, this is going to be the alpha and beta, both will be there. As soon as we perform the operation, left of that particular state is going to be the alpha, right of that is going to be the beta. This is how we are going to define using an instantaneous description. Next comes three ways are there. Which are the three ways we have seen? First is by transition table. Then next by instantaneous description, and then by the transition diagram. These are the three different ways to represent the Turing machines. Say for example, now given the following ID, this means one of the problem and it is very much helpful for the GATE exam like that. So given the following ID of a Turing machine and Q delta Q2 comma A is equal to Q3 B1 R is the transition. What is the next ID? So what does it says here? You are in the state Q2, input is A5. So what we need to do? We need to change the state to Q3, replace A5 by B1, move the cursor to right direction. You check here, Q2 A5 is there. So what it is telling? Replace Q5 by B1. This has to be moved to, this has to be changed to B1 and we have to move the cursor to right direction. Check here. So A1, A2, A3, A4, Q2, A5, A6, A7, A8 is there. So we are, this part is as just now I was showing the previous slide. This is alpha, this is Q, this is beta, alpha, Q, beta. The machine indicates that you are in the state Q2 and the next symbol to be scanned is A5. And what we need to do, what operation has to be performed? Replace Q2 by Q3, A5 by B1 and move the cursor to right direction. So the machine enters into the state Q3, the current input symbol to be replaced is B1 and R indicates the read-write head to be moved to the right side of the transition. So A1, A2, A3, A4, B1, this has been moved to the right of that one, Q3, A6, A7, A8. This is a representation made by the how actually the moves are made. The transition diagram, how do we represent this with a transition diagram? So as there are three different ways are there, I told instantaneous description, transition table and transition diagram. In the transition diagram, we are going to, what all the number of states we have, those many number of states we are going to represent. As we know, we are going to represent the states by the circle. We are representing state by the circle. And what it says here, if you check here, Q0 on 0. If 0 is there, go to the state Q0 itself. So Q0 on 0, it is Q0 itself. And 0 as it is, move the cursor to right direction. 0/0 and move the cursor to right direction. Q0 on 1, we are telling, we go to the state Q0 itself. Let a input be 1 as it is, move the cursor to right direction. If you check here, Q0 on 1 and input is 1 itself, move cursor to right direction. If you see Q0 on B, what we are doing here, Q0 on B is change the state to Q1, replace, let B be as it is, move the cursor to right direction. You see here, Q0 on B is B itself and moving the cursor to right direction. This is how we are going to represent using the transition diagram. Thank you, students. In the next slide, we'll solve a problem on the transition. We'll solve the problem on a